It's a great pleasure to be here. I've been visiting with SAFE for a few decades now. Yes, we are that old. And in fact, it's interesting to have the thing up there because I remember what 25 years ago at PARC, we had in the CSL, when people would give their dealer, there was an app up there where the people sitting in that room could, in real time, tell you how they felt about your talk. So at least we are not there here yet, just the questions. That'll be good enough. So it's my great pleasure to talk to you today about this topic, which really dawned on me as a central topic for research for the next 10, 20 years. A few years ago. I have spent time in a variety of research areas, starting with logic and constraints and concurrency to high-performance programming languages. And a few years ago, more or less driven by the amazing success of machine learning, I realized that from the logic point of view, from the viewpoint of people who work on programming languages and who worry about programming models, we missed out something very, very basic. And that thing that we missed out was, well, we spend all our time talking about programming languages, programming models, how to instruct computers to do what they need to do through explicit programs, explicit instructions. And what the success of machine learning was showing us is that's only part of the story. The other part is training. The other part is learning from large amounts of data. So then the central conceptual question on the table becomes one of how do you bring in the ideas of training and learnability into the very heart of your programming model. And then, of course, how does that change the way that you develop software, your tools, and so on and so forth. But you've got to start at the very basics. So that's really, this is a little story of a journey that has just started. There has been a fair bit of research over the last 10 years or so in the space of logic plus machine learning. And I will cover some of that. But I also think that some of that work, particularly driven by folks coming from machine learning, has not quite had an appreciation for where logic is truly useful and where it is not, and where we need to break the foundations of logic and go to new places in terms of the basic notions of individuation and predicates over crisply defined individuals to a notion of, well, there are some distributions over even what it means to be a city, what it means to be a person, and so on. These are not crisply defined notions, and hence logic as we have understood it from the late 1800s, probably in this modern age of interaction and being completely embedded in the world, also requires a reboot. I will not talk so much about these newer aspects. At the very end, if I have time, I will speak about some work that Radha Jagadishan in Chicago and we have been working together for a long time, but recently we have started this work on differentiable logic as a way of looking at logic formulas as if they are formulas that have derivatives, and therefore you can build up theories which fundamentally are such that there are parameters inside and you can learn with vast amounts of data against it. And perhaps that will give us a way to get at this direction of moving away from logic with very crisp notions of individuation and predication. But let me start from a point of view which, you go back to Nicholas Wirth, starting from programming models. And programs equals algorithms plus data structures at ETH in Zurich was, back in the 70s, the foundation of Pascal and that set of ideas. And then in the 80s, with Bob Kowalski and the group at Imperial College, came the idea that, in fact, algorithms, fundamentally you can decompose, came the realization that first-order logic, and in particular, even a seemingly restrictive subset of first-order logic, definite clauses, are powerful enough to express all sorts of computation without really the requirement of any other procedural framework around it. And that start to logic programming, that start led down the path of, okay, we work with a Prolog-style engine, and we've got some additional notions of control of, depth-first search and particular particular way of doing parallel search that we build in. And so when we think of our programs, we are really thinking of what is their underlying logical content, and then how do we organize the search for the right proof for our query against it. And I'd like to put forward something which places at a more fundamental. So, of course, in the late 80s, the notions of constraints were primarily developed by Kolmar and then the school at IBM at that time, Jean-Louis Lassalle, Jacques Jafar, Michael Maher, the ideas of constraint logic programming showed that, in fact, you get to a much more productive, from a programming point of view, state when you think not just of first-order logic, but you think of interpreted versions of first-order logic, namely constraint systems as systems of partial information about which you are representing information and around which you are consuming that kind of information. And hence, constraints sort of made their way into declarative programming worlds around that time. And I think now, much more recently, we've also come to the realization that in order to deal with the messiness of the world, and this will come into the forefront when we talk about machine learning combined with logic, when you have to deal with the messiness of the world, probabilistic ideas have a really important role to play. In the last 10 years or so, there has been the development of this framework of probabilistic programming. And a number of folks have come at it, again, from an imperative programming point of view, from a functional programming point of view, to embed the basic idea that you need to have some sorts of probabilistic, some sort of random variables, some sort of probability distributions as an essential part of your programming model. And in fact, again, with Professor Radha Jagadishan and some other colleagues, in '96, we had formulated a version of concurrent constraint programming with probabilities, and I will speak about that more as we go. So today, where I stand is a position that these three components, logic as a basic foundation for putting together declarative information about the world, constraints as a way of expressing actually fairly complex algorithms, the constraint solvers, in a very declarative way for use by application programmers, and then probabilities to introduce a notion of uncertainty about what you really are able to express and learn some of that information out of the data. These three things combined, I think, offer an important foundation for our work as we go forward. Daniel sort of stole, well, it's not really my thunder, but stole my slide. What can I say? Even though I just sent him the slide 15 minutes ago, somehow he had the slide in there already in his presentation. I think today it goes without saying that there has been remarkable progress in the last several years, particularly as a result of the discovery that certain sorts of neural networks, the so-called deep learning networks, are able to learn at scale. Now there's amazing work which is able to express neural networks that are hundreds of layers deep. And so essentially the position that we are at is that these uniform algorithms, like the stochastic gradient descent algorithms, are able to propagate their signal through hundreds of layers of processing and still get something meaningful out of it. So there's a tremendous amount of progress driven by the availability of data, the availability of computation, the discovery of newer techniques. And I'm not going to dwell on this. I think Daniel already pointed out some of the advances that have been made. In a nutshell, you can look at that as, at a very, very high level. If you look again at a programming model point of view, you look at some very basic things like the lambda calculus. What is it about? It's just about parameterization and substitution. So you look at supervised learning. What is it about? At the very essence, it's really a pretty simple setup, a setup that says you've got some amount of training data, you're looking at a function that you don't know what it is. And you're looking to find out what more about this function by training it against data. What kind of data? In the context of supervised learning, you've got some input-output pairs, the x's and the y's. The x's and the y's are a set of these. And what mechanism do you have available to learn this function? You have this notion that the function that you're interested in ranges over a large space of functions and in a parametric way. So there are a certain set of parameters, t here, which as you can vary the set of functions in this space, you can enumerate. And so now the task becomes, and you're given a loss function, which tells you the difference between what the prediction that your current function with its current parameters makes from this input and the difference between that and the output that is associated with it in the training set. So you have a loss function. With this basic raw material then, there are algorithms which essentially let you figure out, provided that you can compute certain partial derivatives, let you search in the space of parameters for a parameter that, for a setting, a parameter that optimizes the given loss function given the data available to you. And the advantage of this particular style of approach has been that it's very GPU friendly. And so you're able to perform tremendous amounts of computation very, very quickly, and hence work on extremely large data sets. And you need those large data sets because the kinds of models we have are in fact very simple models built up from so-called neural elements where there's some sort of linear combination going on at each layer together with a non-linearity. And that is essentially the very startling point about all of this. We are actually working in a context of non-convex optimization, and hence this kind of minimization could in principle get stuck at a lot of intermediate minima, but in practice this does not happen. And so one of the, as I was telling Daniel earlier, from my point of view, one of the big advantages of where we are today is that there's been so much progress on the application side that some real theoreticians have gotten involved to try and figure out what is it about these application landscapes that allows these seemingly weak techniques, which shouldn't really work theoretically, to work. And so there's some very nice work coming out from a variety of researchers that establishes that, in fact, in many cases, the situation we are in is that the local minima all share some nice characteristics, and getting to any local minima is adequate for our purposes. But this is not enough. I'm going to contend that machine learning, even with all the enormous progress that we have made recently, is not adequate. And I will get to that by talking about, look at the set of cognitive tasks that have seen major improvement over the last several years. We have seen enormous progress, but the progress is in the context of the innermost layer, in the context of perception-related tasks. And there is so much more to do all around it, even going out to understanding technical documents. So today, IBM TJ Watson Research Lab that I work at, we have a business division, the Watson Business Division, and one of the things that we are able to do is ingest a very large number of documents. For example, in cancer, and so are in a position where we can keep on top of the tremendous amount of new work going on, coming out almost every day, every week, and are in a position then, by ingesting that information, to be able to synthesize some more abstract information and advise the doctors interested in handling a particular patient with a particular set of symptoms on what the right approaches to treating that patient might be. This ability to ingest vast amounts of data and make sense of it. In order to get there, today we are able to use only fairly, let me say, shallow techniques, bag of words techniques, techniques that associate, word vectors with words and, with phrases and with sentences. But you're not able to understand the deep meaning of phrases. You're not able to understand what not means in a particular context and how that can completely change the meaning of the word. So we're far removed from really understanding technical documents. By understanding technical documents, what I mean is understanding, say, in the machine learning literature or the computer science literature, being able to discuss, ingest, and understand these documents at the level of being able to discuss with a professor in the field the content of that paper as a graduate student would be able to do. And that is, in fact, the vision that we are headed towards. It's a vision of professional assistance in deep domains. And by deep domain, I mean essentially any domain in which there has been a vast amount of work, years, decades, in some cases centuries of work, which has caused, therefore, a significant amount of knowledge to be built up. And the challenge then is, how do you ingest that knowledge and work with an understanding of that knowledge while still taking advantage of all the data-driven abilities that machine learning brings to the table? We've named this project the Upton Project after one of the primary assistants to Thomas Edison. And the notion was that Edison, of course, was a famous inventor, but he relied on the skills of a lot of other people to do their work. And so we think of this kind of a computational system as an assistant that helps professionals in various disciplines be able to do their job better by being able to understand the content of the knowledge within that domain and being able to engage with the professional. So imagine what level of flexibility, what level of creativity, what level of understanding would need to be exhibited by such bots in order to gain a PhD from let us say, a reputable university. So that brings us to the viewpoint that when we talk about this box, that before this, the slide I had up there had a neural network in here. And the neural network is made up of a large number of layers, but those layers are all made up of extremely simple computational elements, linear combinations and some nonlinearity on top, elements that know nothing about the domain on which we are working, in which we are building up this function. So what if, in fact, we are able to work, and so the consequence of that is that in order to train these networks with a very large number of parameters that know nothing about the domain, you need a vast amount of data. And then that significantly reduces the applicability of these techniques because, well, you don't have a vast amount of data sitting around in, pick almost any deep domain, picking, say, the notion I was talking yesterday about another area that I'm working in, compliance, and you pick the notion of a lawyer who needs to understand the latest developments within the EU regulations that govern, capital equity ratios. Very specialized subject. There simply isn't terabytes of data available about that subject. And yet, we wish to aspire to a setting where our computational agents are able to understand that and deal and offer valuable help to that professional. And so in that case, the idea here is think that, in fact, what we have available is not a neural network, but a theory. And we will talk very soon about a probabilistic theory, and a theory in which those programs themselves are differentiable, and therefore in a position where, since you're expressing so much more information about the domain, the need for weak techniques, which need tremendous amounts of data, that is somewhat reduced. There's been recent work by Lake and Salakhodinov and others pointing out that in tasks such as recognizing digits, hand-drawn digits, it really helps to have some kind of a generative theory of the domain. Then you can work with very small amounts of data and make progress. That is the basic idea that we are after, developing a framework for programming in which you're able to express significant amounts of prior information in a way that is compatible with using machine learning techniques. I will give you some very concrete examples of places where already significant progress has been made along these lines. So semantic parsing is an area where, fundamental to the application of logic in a variety of human disciplines is the ability to elicit information, structured information, logical information from natural language text, and to answer questions based on that. Now, of course, as the Jeopardy system from IBM showed, in certain areas it is possible to answer questions, such as in the game of Jeopardy, without knowing a whole lot about the underlying domain. For example, without even knowing that Toronto is not an American city. You can still answer questions and still win a lot of money at a game like that. But that is not true in deep domains where, in fact, knowledge of things that are true about the world. For example, you're working in a database and you're asking questions about geographical facts. And here knowledge, questions such as how many rivers do not traverse the state whose capital is Albany. This is the state of New York. This might really be helped with a lot of background information about the various states and the capitals and where rivers flow. And working with just information at a statistical level available today with shallow techniques in natural language does not give us access to that kind of information. So there has been work in semantic parsing. Semantic parsing is the area which starts with utterances and obtains semantic forms. Semantic forms are some sorts of logical representations. There are a whole variety of semantic forms you can use, prologue style, first order representations, or full lambda calculus terms. And the question is, given a collection of such utterances paired with semantic forms, can you actually learn the parser that will, at runtime, given an utterance, produce the corresponding semantic form? And there has been significant work in this space with actually not bad results in a number of data sets. And fundamentally, what is going on here is that given this data set, the learning algorithm actually learns the grammar in this domain and learns the probability, it's a probabilistic grammar, and learns the probability distributions across the productions of this grammar so that those utterances that are paired with the right, that are paired with meanings, those utterances have a high probability of succeeding with this particular grammar. Ideas very reminiscent of inductive logic programming from 20, 25 years ago. And in fact, the techniques used, for example, in the work on CCG are very reminiscent of logic programming techniques. The connection between parsing and logic programming is a very old connection, very reminiscent of logic programming techniques in learning these productions. So again, here, nothing is given in principle about your original domain in terms of the productions, and all the productions are learned purely from the forms such as these that are given in your data set associated with your utterance. An advantage, and we have seen this, we are working with semantic parsers for our own application domains, we have seen this, an advantage of an approach like the CCG approach is that you can seed the system with an initial lexicon that says this word is associated, it contributes this semantic meaning, and there are a whole bunch of these productions. You can start out the system with that information. And then via training, you are able to get much better results than if you start without that information. Of course, if the initial information is incorrect in the sense of being inconsistent with the data, you're not going to progress very much. But this is an example of a domain in which significant progress has been made using the sorts of techniques I'm talking about with the combination of logic and probabilities. Okay, here is another more recent domain. And this is a domain of PDF extraction. So again, if you're going to ingest the world's knowledge, you're going to have to deal with PDF. It is more or less a pervasive document format. And the problem with dealing with PDF was designed to reproducibly and to reproduce across a variety of presentation media marks on paper in an accurate way. So it's all at the level of placing ink on paper. And out of ink on paper, I need to figure out where are my footnotes, who's the author of this paper, what is the subject, title of this paper, where's the abstract, if it is a legal document, what are the obligations, a whole amount of application level structure. Tremendously hard problem. One of the ways in which some of our researchers are going after this problem is in fact associating a theory, and this is the important point, when you work with just logic, without the ideas of probability, you're more or less forced to write down what is true about the relations of interest to you. But when you work with real-world examples, it's very hard to find something that is incontrovertibly always true. So the leeway that probability gives you is the ability to work with rules, axioms, formulas that are plausible, not necessarily certainly true. And it's that plausibility that gives you significant wiggle room to write down a bunch of covering axioms within which is what is actually right, the data guides you to that. So here also, these rules that are written down that connect the possible placement identification of this rectangle, is that a caption? Or is this rectangle actually a label on the XY axis? You can write down a bunch of rules, each of which are falsifiable. but with the notion that there is a probability distribution across these rules, and that distribution is what you are going to learn, you're able to make progress on a task like this. So that brings me now to a central point, which is there has been work on things like Markov logic networks, which, again, as I said at the very beginning of my talk, is driven more by folks from machine learning looking to realize some of the power of logic in the context of machine learning. And what is the power of logic you're after? The power of logic you're after is that there are relations. That is a way of taking groups of individuals and bundling them into relations and providing partial information about these relations. And then information such as, implication, this relation, conjunction of these with some elements existentially quantified is contained in something else. So that's really the power, and there's been a lot of work, not just Markov logic network, but also Lise Getou's work on PSL in that space, but it has a little bit been disconnected from the development of logic as a foundation for programming that we saw coming out of the logic programming world, and that was developed also in the context of concurrency many years ago. And so my goal here in the next few slides is to show you how we can bring this stuff back together by starting with a logical system that I have been working with for a very long time, which captures at the heart of it a simple theory of conjunction, disjunction, existential quantification. This is the area of concurrent constraint programming, and the way to look at it is that we have a certain simple sets of formulas. These are formulas that are closed under conjunction, under a certain kind of entailment, under existential quantification. And what we have available is an entailment relation, which is also an execution relation, that tells us how we can extract more information out of these formulas by essentially applying these very, very simple rules. And these are all logic-based rules. So in fact, if out of an initial configuration of a certain set of formulas, you're able to derive a certain constraint, then there is a logical relationship that holds between them, namely the initial formula implies these constraints. And the power of this sort of framework is such that it already, of course, incorporates things like conjunction and disjunction and constraints that are the heart of constraint logic programming. So it's very easy to write down a sort of an absorbing interpreter, which shows you how you can embed something like constraint logic programming within a setting like this. We have spent a fair bit of time on this framework over the last many years, and the main piece of work that is related to my talk is the work on probabilistic computation that we did in the mid-90s or so. So before I go there, let me point out that one of the advantages of going into a richer logical framework which embeds the ideas of constraint logic programming is that the work that has happened in machine learning in the context of constraint logic programming, such as inductive logic programming, you can now ask in this richer setting, what does that mean? To give you an idea of what that question boils down to in this setting, it turns out, and again, I don't have time to go into the details, but it turns out that the sorts of programs that I quickly showed you on the previous slide correspond to certain functions that are called closure operators, operate over a space of partial information, and they only add more information, and they keep adding it until they reach a fixed point. So those closure operators are characterized by a set of elements called the fixed points of this function. Once you have the fixed points, you know that function precisely. Now that, therefore, gives you a context in which you can ask, I am given just observations. I only know that certain elements in this domain, certain constraints, are fixed points of this program. I don't know what the program is. And I know that certain other elements are not fixed points. They are, progressive points of this particular function. As long as this information is consistent with each other, meaning there is some closure operator that can realize this, the question then becomes, can I discover the syntactic presentation of that closure operator, which is the same as saying that I can discover the underlying program which provides this sort of observation. And again, this sort of thing can be done without any notion of probabilities introduced into the picture. And it's a question of you're learning the relational structure of your domain here by learning certain sorts of closure operators. In the context, and just a quick aside here is, I've done, in my career, I've done sort of some major pieces of work around the extended programming language and CCP. But another piece of work that I'm very proud to be associated with was led by Ras Bodek and Armando Solar Lezama, and that's the work on sketching. And it's the same old idea. The idea of program synthesis is very old. It goes back to Cordell Green and company in the 1960s, but we went about it at that time in a very different way. This more modern idea of sketching is that you write programs, but programs with holes in them. And then you leave it up to, in this case, in Armando's work, you leave it up to a constraint solver to, from the surrounding program text, flow constraints into what could be the piece of code that fits into this hole such that the overall system does not throw an error or satisfies some given constraint. And this has been a remarkably successful piece of work. So for me, this also is a point in the direction, this points in the direction of, look, as programmers, we should stop pretending that we have complete information about the code we wish to write. Instead, we leave holes in there and we use other techniques to fill those holes. In the case of Armando's work, these are logical techniques to fill the holes. And what I'm going to talk about now are, in fact, non-logical techniques, machine learning techniques for filling these holes. So how does one introduce probability into the very simple setup that I showed you on the previous slides? Actually, it turns out it's not at all difficult. The way you introduce probabilities is you introduce a certain goal, we'll call it a sampling goal, and it says, here is a variable, and we're going to sample it from some probability distribution. And we did this in '96 before the probabilistic programming work took off. And in essence, what happens when you get to execute this goal is that you choose, this is called the sampling interpretation. Please don't take it literally. It's a way of getting the semantics understood, but in reality, to get any kind of efficiency, you have to use much more sophisticated techniques for execution. But in any case, what you do at this level is you sample the probability distribution, get a value t, add the constraint x equals t to your system, and progress. Now, here's the important point. The way that I'm thinking of my problem, I've got a large number of random variables over independent random variables over probability distributions, but then I use constraints in order to link them up, in order to specify conditions that say they can't just independently take these values, they must satisfy certain relational conditions. That is the point of these constraints. And this is why within the framework that I'm talking about with constraints and logic and probability, these ideas turn out to be quite powerful because, of course, what you now do is that if those constraints cause inconsistency, then this execution path that you were on, where you randomly chose a value for this variable and that variable, that path does not exist. It disappears. And this is very similar in logic programming to having to backtrack in the case of failure. So then what you do is you simply look at the consistent executions, and you will get back a constraint at the end of each execution. You look at the whole space of answers you get, and you associate, and you have to do this many, many times. You're sampling. So you sample many, many times. The relative proportion of these answers, this gives you the a posteriori probability distribution over your answer set. This is what the whole program was set up to do, was to specify what this a posteriori probability distribution needs to be. And this simple way of tying up the constraint-based, concurrent constraint-based operational semantics with the notion of sampling from a probability distribution gets you a probabilistic language in which you have that flexibility that I talked about earlier, where you can specify rules that are plausible but not necessarily precisely correct. Turns out this generalizes to a whole bunch of other settings. We introduce time, discrete time. We believe it generalizes also to hybrid time, where you've got a notion of continuous as well as discrete time, but this has not yet been done. There are some simple examples that illustrate the idea. I'm going to skip these because of lack of time, but my slides are available so you can go into the details. Prakash Panangadan also got involved, and in work in Popple 98, what was shown was that you can actually generate continuous probability distributions using recursion, provided that certain conditions are met on the sorts of programs that you write, such as you're only reading in AST and you're not writing into them. Now you can go back and look at the standard examples of modeling, probabilistic logical modeling in AI, and see how they can be written within a framework like this. So BaseNet, that shows up as, here's Julia Pearl's classic example, that shows up as you've got variables like chair, sport, and so on, that are random variables. They range over a probability distribution, which is given concretely here, true with this probability, false with that probability. And then you have a bunch of logical formulas which are essentially imposing constraints on them. In this particular case, if chair is true, then worker is sampled from one probability distribution. If chair is false, then worker is sampled from another probability distribution. So you get the kinds of Bayes networks with acyclic dependence on random variables, fairly easy to express. And similarly, a large number of other kinds of things, Markov models, Markov fields, hidden Markov models, Markov chains, and certainly stochastic context-free grammars can be expressed in a framework like this. I will skip this. You can also, unlike Bayes networks, which are sort of focused on a fixed set of random variables, the framework that I'm talking about makes it very easy to have, and essentially using recursion or using extension across time, as in the timed case, makes it very easy to have an unbounded number of these variables and constraints connecting these things up. So the so-called dynamic Bayesian networks can be handled without changing anything at all in the underlying logical framework. There is a little derivation which is coming out in a AAAI workshop with paper with Christina Cornelio and me that shows that even something which on the face of it looks very different from the sort of framework that I'm talking about, Markov logic networks, we can in fact turn around and look at them, embed Markov logic networks within our framework. So what are Markov logic networks? This is work by Pedro Domingos and authors and colleagues, and it is a way of combining probabilities with logic, which goes by, look, let's develop a certain set of formulas. This is, again, the sort of background theory. And with these formulas, we're also going to associate certain weights. So we are given FIs, and we're given FJs, and we're given the weights WJ, and then we're going to fix a set of constants. Why are we doing this? Because our intention is that these formulas are to be interpreted over some underlying structure. And we're going to fix the arity, fix the cardinality of the domain of that structure. So that's given by these constants C1 through Ck. And now, once we have done that, we have a way of measuring how probable a particular world is. And what we do is we compute the probability of a particular world by looking at the groundings, by looking at the ground facts associated with the logical vocabulary that these formulas are written in, an assignment of true or false to each of those ground facts, and then we look at how many times a formula is instantiated in that particular world. That gives me an NJ multiplied by WJ, combine those things, that is an estimate of the probability of this world. So on the face of it, what we are doing here is something very, very different from what I showed you working with constraints and concurrency and agents that are reducing, because I am now looking at an interpretation in the real world and counting the number of occurrences of these realizations of these formulas in that world. There's a simple example which Pedro and others talk about, where you have rules such as friends of friends are friends. Again, these are plausible rules. It's not necessarily the case that they're universally true. And then friendless people smoke. Smoking causes cancer. They are associated with these sorts of weights. And so now you can work your way through, look at a particular domain, look at the ground atoms, look at the formulas that are realized the number of times, and you'll come up with an estimate of the probability based on the formula that I showed you. The downside of this approach is that, unfortunately, syntax matters, because suddenly you've introduced a notion. Again, it may be plausible from a machine learning point of view, not so plausible from a logic point of view. You've introduced the notion that you're going to count the number of instances instances of this formula in this particular model. But of course, the formulas that you have, the syntactic form determines, the syntactic form can vary while the formulas are semantically equivalent. So you get 5 formulas, and now you get 5 times as many instances, and the numbers are suddenly completely different. In other words, the answers you will get here are not invariant under logical equivalence, which is not a nice situation to be in. And furthermore, from a very practical point of view, you face this combinatorial explosion of grounding out everything. Nevertheless, my point here is less to expound on the downsides of Markov logic networks as to point out that if you adopt the point of view that I had earlier, where I looked at logic as a programming framework, I was not so much worried about the interpretation of those formulas in the real world, but there's a simple programming methodology that says, look at your independent variables, find their probability distributions, look at how these are related to each other, write down those constraints. Once you do that, you can, in fact, take that Markov logic network that I talked about and convert it into a CC program with ask and tell formulas exactly as I had before. And essentially, what I have is a little meta interpreter for arbitrary first-order logic, a clausal sort of form of a certain negation normal form of logic, a little interpreter written out in these V clauses, which are completely legitimate CCP programs. Using that, I can count the number of times that these random variables, which are random variables that correspond to instances of a ground instance of each of these formulas, I can count the number of times that these variables go down the true branch, and the probability associated with that is going to be determined by this weight. And so I have a way of computing exactly what the Markov logic networks are trying to compute. But by going through this, I have illustrated that the particular things that they are doing, which is really expanding out the whole space of these of realizations of these formulas, that in fact shows up directly in the program that is used to implement these things. And now you can ask the question, why? Do I really need to do that, or can I do some other approximation? So let me stop with just a couple more slides, and I am also running out of time. What I have shown you so far is hopefully a fairly simple logic-based formalism that has probabilities in it. And what I have not discussed at all are the hard problems. When you start combining this with machine learning, the central questions are, how do you learn those probabilities? And if you've got a probability distribution like I have, the sampling interpretation that I talked about at the very beginning was just to set up what it means to run such a program. In reality, you want very efficient techniques for computing for a given query the most probable answer for that query without enumerating all of those answers. So those are the hard algorithmic questions. In the context of stochastic logic programming, which is a related framework, there has been some progress made by James Cousins and other researchers on using some of the standard techniques from Della Pietra et al. And Reiser's work. But it's very clear that in the richer logical setting that I'm talking about, there is significantly more work that needs to be done. There's also personalized PageRank work much more recently by William Cohen that is squarely in the space of techniques that can be applied in this domain. So actually, I am going to stop here, and I didn't even pay attention. This audience is not very social. There are no questions for me. So I will leave this slide up in case there are any questions, and I can address that, but otherwise I'll stop and take questions.
Okay, so let's thank Vijay. And we have time for some questions. Yes, over here.
I just have a question, because all these are focusing on the probability of an event based on a huge amount of data coming. And my question is, actually, facing on a big amount of data, the really first problem is how to read the data without creating any misunderstanding, because the data arrive on a completely unpacked and unformatted way. So you mentioned before the PDF. Very stupid example for me, but I mean, let's suppose the PDF is actually created by scanning. Then all your input is unapplicable. And the likelihood that you try to calculate are then restricted, so to say. And the validation of the program itself is going to be in somehow on a critical point of view. So basically my point is how much job has been done in order to actually recognize the data, because the data arrive on a completely different format.
Of course. There's no question about it. There are some very, very deep problems here in what is in the data to begin with, what kinds of implicit biases are in the data. And media today is rife with stories. For example, the Google face recognizer, it was not able to, it confused certain animals with certain humans. You know, there are all sorts of biases that come from the training data. Uncovering, finding those, correcting for those. It's like the news stories, the fake news stories on Facebook. Very, very hard problem to figure out what truth really is in a society of humans with very different viewpoints on various things. So I don't have anything really fundamental to say there, except that the notion of explainability has now come to the forefront. DARPA is investing, in the US, is investing a significant amount of money in a new program for explainable AI, where the notion is it's not just good enough to say yes or no, or gorilla or human. You've got to explain why you are doing that. And here too, obviously, I feel that the kind of logical systems that I'm talking about will hopefully have a better chance than everything is expressed purely in the form of some sorts of weights in a massive system. So we will see. There is a lot of hard work to be done, because what is an explanation is itself a fundamentally human thing. What's an explanation for you might not be an explanation for someone else who understands the subject at a different level of depth. So lots of really hard questions there.
Right. So a quick question here. Yeah.
Regarding the probabilistic CCPs that you mentioned. You mentioned on the previous slide that you also consider sampling techniques.
That's right.
So, and the question is, in many cases, I expect the original probabilities that you have are not, say, the true, but they are estimated probabilities. So they are not very exact. So shouldn't that, in fact, speak for using sampling techniques? Maybe you're not really requiring the exact solutions, but rather approximate solutions are good enough.
Yes, so one has to distinguish two sorts of phases with a program like this. One is the training time, and the other is execution time or runtime. So the sampling techniques I talked about are of use at runtime, once you have the probabilities learned either through the data or provided explicitly by humans. And even there's lots of approximation going on. So there's really, this is the price you pay for moving to this richer representation, is that you're working with approximations and you may make errors. And you may make errors that are very hard to discover that you made an error. That's the really insidious part about this. And so I think these are just some of the hard questions that need to be dealt with. Don't have any specific ideas on how to approach them yet.
What time perspective do you foresee for the development of from perception over reasoning to intelligence?
So I have a flippant answer to the first and then a more serious answer. So the flippant answer is this. When I was younger, the answer to that question was always 20 years. It's 20 years away. Next year, it's 20 years away. So you never get to that horizon where you get real AI. Now this is the age of deep learning. So the answer changes. It's 10 years away. Every year, it's 10 years away. Yeah. Right. So it's so hard to predict these things. And the reason it's so hard is because obviously a very large number of things need to come together to make these breakthroughs. So I have a very pragmatic way of looking at it. I can look at it from a theoretical point of view, and it's clear. It's sort of, they're so difficult, these questions of getting, I talked about three circles, the inner circle, the second, the third circle. The third circle, an example of how complex, how difficult it is I call this the Ruth Bader Ginsburg test. She's a Supreme Court judge in the United States. We often worry about understanding meaning of natural language sentences. Well, what is the extreme of that? The extreme of that is making meaning. How do you make meaning? In the US, the Supreme Court makes meaning. I talk about legal meaning here. So look at any of the Supreme Court judgments. These are enormously complicated natural language generators. They are enormously complicated documents, very closely reasoned, situated in the context of legal, political, social history of the United States. Imagine a bot being able to produce a document like that. Take any of the classic examples of Supreme Court judgments. If in my lifetime that gets done, 30 more years, let's say, that would be a significant accomplishment. So that's the theoretical side. On a practical side, the way to look at it is this. What is driving AI today is a lot of successes with a tremendous amount of industrial money pouring in. For industrial money to continue to pour in, you have to have a string of short successes, places where you're able to get humans to do their work much more quickly, efficiently, or as I was pointing out in the case of the cancer studies, tasks that they have not been able to do before. As long as we can keep finding a succession of these, that money will keep flowing in. Money keeps flowing in, that means a lot of minds get attracted to this field. That means the opportunity for breakthroughs is even better. So I think within the context of IBM, we have invested heavily in getting a platform out on which we can do tremendous number of experiments quickly. And so I am really, hopeful that because of that, we'll be able to get to those sorts of questions. But still, my real answer remains 10 years.
So in relation to that, basically, and we've seen the hype around machine learning and AI and so on increase really, really rapidly the last few years.
Yes.
Do you think we're running the risk of getting into another AI winter, basically?
Yeah, certainly. I think, again, the AI winter really came about because the funding agencies stopped working.
Yeah.
But the new dynamics, it's not the funding agencies, it's the businesses, the enterprises that are pouring money in.
Yeah.
And they'll keep pouring money in as long as there are customers willing to pay for that stuff. So I suspect the winter, I do expect a certain retrenchment of optimism.
Yeah.
In the AI field in the near future, again, as we realize that there's still very, very hard problems out there. But if we have the right platform set up, if we are still able to do some experiments successfully, I suspect that some companies at least will be able to continue investing in this and progressing. So it may not be a winter the kind we have seen before in AI, at least in the United States.
Yes. Good to hear. It's nice to be popular. Shall we take the last question? What theoretical framework do you base your cognitive task landscape on?
Yeah, that's a good question. No, in fact, this was a hard one. We sat down and we did it out of contemplating our navels. But then I went and looked, and I asked various cognitive computer scientists the question about, do you have a taxonomy of tasks, which goes from, what I wanted to do was to get a sense for a human to become a professional. It takes about 20 years of education, starting from kindergarten. So there are stages that you go through. And so what I wanted to get a sense for was, what are the questions asked at each stage? What capabilities, what techniques are you learning? For example, how to ask questions is an important capability. And the short answer that I got was that there isn't such a ladder. So if anyone here does have references and ladders that I can use, I'd really appreciate that. There is a Bloom taxonomy on skills and different occupations. We looked at that only coarsely approximates what I had up there. So yes, I would welcome any input from people here about theoretical frameworks to look at to do a more systematic study of that work.
Okay, so let's thank Vijay and Boxen again. And